air above the mountains is in constant motion. But what exactly is happening there? Why is it hailing right now? Where does the flooding come from? What's going on in the sky? An enormous international research team aims to get to the bottom of these questions using an entire armada of measuring devices. Ultrasonic anemometers, laser-based remote sensing from the ground, and flying measurement stations in the air. The TEAMx research program focuses on how air exchange processes occur over mountains and how these relate to local, large-scale and global weather phenomena. The goal? Better climate models and more accurate weather forecasts for mountainous regions. A cornfield, a forest, an alpine meadow. The air behaves differently over various types of terrain and land use. When the sun shines on a forest, it's not the same as when it shines on a meadow or a lake. Different surface properties lead to varying heat absorption, heat release and evaporation, which in turn influence air movements and thus the formation of wind and weather. And this can be measured. Over 200 researchers from more than 10 nations are joining forces under the TEAMx research program to closely examine weather-causing processes in mountainous regions. Over the course of a year, data is being collected in the valleys and mountain ranges of the Alps, as well as in the Alpine foothills. This large-scale measurement campaign involving over 40 partner organizations occurs on this scale only about once every 25 years. It is coordinated and led by Manuela Lehner and Matthias Rotach from the Department of Atmospheric and Cryospheric Sciences at the University of Innsbruck. To understand the bigger picture, the focus initially lies on small-scale effects. It's not about the flap of a butterfly's wings that could trigger a storm, but it is about tiny air movements.
One
example is turbulence, the turbulent exchange of heat from the ground into the atmosphere, up to larger scale processes like slope winds that transport water vapor upwards, and even very large-scale processes such as the flow of air over mountains, like the Alps, which can lead to phenomena like föhn winds.
Turbulence. Many people have experienced it on an airplane, but it also occurs near the ground. Turbulence arises when air masses mix irregularly and chaotically, causing changes in wind speed, direction, and air pressure. These air movements, these swirls, can be very local and small scale. In meteorology and atmospheric sciences, they are of great significance.
Turbulence is one of the last unsolved problems of classical physics, but in the atmosphere is the dominant process that contributes to this exchange between the surface and the atmosphere. And although we have relatively good theories that describe how turbulence behaves in flat terrain, we definitely don't for mountains.
This is a major problem when it comes to accurately predicting weather and climate development in mountainous areas. This is where TEAMx, with more than 200 researchers, comes in. It is important to understand the processes both at high altitudes and very close to the ground.
Because the Earth's surface is essentially the driving force behind atmospheric movements, it provides the energy which is absorbed through solar radiation and then released into the Earth's surface. This means that many processes in the atmosphere depend on how these interactions work. And these interactions are naturally more complex over complex topography because there are regional wind systems and flows that influence this exchange.
Everything is much more complicated above the mountains than over flat land. Weather models, computer simulations fed with large amounts of data, are used to create weather forecasts. These help us understand and predict atmospheric movements.
Diese Modelle, das wissen wir, die basieren
We know that
auf
these models are based on physical principles. But these principles were developed for flat terrain over the last, say, 100 years. And we obviously know that it's not flat here, and there are studies on what might need to be improved. What we've achieved with this program is bringing the entire community together in one place and at the same time to tackle these problems collectively.
zur gleichen Zeit versammelt und haben diese Probleme gemeinsam in Angriff genommen.
More than 40 institutions are involved in TEAMx, including universities, research institutions and weather services. The University of Leeds, Meteo France and the German Aerospace Centre DLR are all part of the effort. They are united by the desire to use new data to improve weather and climate models for mountainous regions, making forecasts more reliable.
Based on this data, we can now better understand the wind and flow conditions in the Inn Valley and its side valleys, as well as the transport of air pollutants between the Inn Valley and the Alpine foothills. In mountainous regions, the dynamic and chemical processes that determine the level of ozone and fine particulate matter in the valley atmosphere are particularly complex.
Climate change is already causing noticeable effects in the Alps. The average temperature is rising faster than in other regions. Weather events are becoming more intense. Glaciers are retreating. Landslides and flooding occur after heavy rain, and wildfires break out during dry periods. Over the course of a year, comprehensive measurements are being taken in the Alpine region to study the processes involved in weather.
The measurements are being conducted in a fairly large area, along a roughly north-south cross-section through the Alps, from Lake Garda to approximately Munich, with intensive measurements focused on 4 areas. One is the Alpine foothills north of the Alps. The second area is the Inn Valley, then the Adige Valley, and in between, the main Alpine ridge. The idea is that the Adige Valley and the Inn Valley are similar in size and also have comparable urban areas, such as Trento and Innsbruck. The difference is that the Inn Valley runs approximately east-west, while the Adige Valley runs north-south and lies south of the main Alpine ridge, whereas the Inn Valley is north of it.
This allows for comparisons and corresponding conclusions. The Austrian city of Innsbruck is located in the Tyrolean Inn Valley, at the boundary between the Northern Alps and the Central Alps. The Northern Alps and the Alpine foothills are strongly influenced by weather systems coming from the west. When moist air masses pile up against the mountains, this leads to abundant precipitation. In the Central Alps, however, it can be relatively dry. Another common effect in the Inn Valley is föhn, a warm wind that, during strong southerly flows, can sometimes still be felt as far as Munich. The Southern Alps, or Northern Italy, are influenced by entirely different factors. An important partner in the TEAMx consortium is the University of Trento. The Italian city is located in the Adige Valley, less than 30 kilometers northeast of Lake Garda.
In the Southern Alps, the mountains are facing a very broad plain, the Po Plain, and mostly also the sea, the Mediterranean Sea, on both sides, in particular the Adriatic Sea. So airflows coming from those regions are affected by a typical Mediterranean climate, so typically warmer climate, but also moisture. Features connected to these situations are, of course, sensitive to these geographic elements.
Similarly to Innsbruck, also in the southern slopes of the Alps, we can have föhn wind, in particular when we have synoptic wind coming from north, and so we have a channeling of the wind, for example, inside the Adige Valley. So similarly to Innsbruck, we have föhn wind, but with the opposite direction with respect to Innsbruck.
To obtain precise data, the existing, already well-developed network of measuring stations, such as those around Innsbruck and in other regions, is being expanded as part of TEAMx. more details can be captured. This means there are more measuring stations at shorter distances from each other. The focus is on the detailed investigation of the mountain boundary layer, the part of the atmosphere influenced by the underlying mountainous region.
So during TEAMx, we had very intense observations with a network of turbulence towers, also measuring turbulent pressure at multiple locations that can give us really very detailed information about turbulence on a smaller scale.
Weather stations measure near-ground effects. Measuring towers, like the one in the Tyrolean village of Kozas in the lower Inn Valley, can capture data in the lowest layers of the air. Various measuring devices are used to determine humidity, temperature, air pressure, solar radiation and air movements, both nearby and at a distance.
We installed towers with different levels of measurements, up to 9 or 12 meters above ground. We also had instruments measuring concentration of particulate matter to monitor the transport of those substances in the atmosphere.
For a more precise picture, measurements are taken at numerous locations over the course of a year. Small-scale effects, for example, are measured using ultrasonic anemometers.
These allow us to determine wind speed, direction, and actually three-dimensional wind components with a resolution of 20 Hz. That is, 20 measurements per second. From this, we can actually measure these turbulent transports. The turbulent eddies responsible for the transport of heat from the ground into the atmosphere, as well as moisture and evaporation.
Remote sensing systems are also used to conduct measurements over greater distances and heights, for example with Doppler winds Lidar. Lidar stands for light detection and ranging. Using laser beams, wind speeds and directions can be measured at distances ranging from a few hundred meters to several kilometers. This is important for understanding air movements in their entirety.
Die senden einen Laserstrahl aus im Infrarot.
They emit an infrared laser beam. This beam is reflected by aerosol particles, dust particles. And if these devices also have a scanner that can focus the beam in different directions, we can capture the three-dimensional structure. Of course, we also use flow simulations to complement this.
Natürlich auch Strömungssimulationen ein.
These help complete the overall picture. In Trento too, researchers are seeking answers. The goal is to better understand the energy exchange between the sun and the earth, the engine of the weather.
The surface energy balance is how the energy arriving from the sun is divided in different components. For example, the sensible heat flux, the part of the energy which is used for rising the air temperature, the part related to evapotranspiration, the so-called latent heat flux, and the part going into the surface.
The permanently installed devices measure at various locations over the course of a year. In addition, there are two large multi-day intensive measurement campaigns, one in winter and one in summer. At more than 15 locations in the Inn and Adige Valley in the Central Alps and in the Alpine foothills, drones, airplanes, weather balloons and other devices capture particularly detailed datasets. 3 research aircraft from Germany and the UK are deployed during the intensive weeks. They are stationed at Innsbruck Airport, from where they launch their various missions. They fly over areas multiple times at different altitudes and in different directions. The British aircraft is the FAM Airborne Laboratory, which is specialised in atmospheric research. Additionally, 2 Cessnas are in use, one from the Technical University of Braunschweig and the other from the German Aerospace Center DLR.
Eine Wetterstation steht lokal an einem Ort. Damit können wir
A weather station is located at a single point. With it, we can measure temporal developments very well, but we lack spatial information. Aeroplanes, on the other hand, allow us to fly along the valley axis or across it to obtain spatial information. And with the larger aircraft, we can also fly over the main Alpine ridge, capturing large-scale information.
Auch großskalige Information zu bekommen.
The DLR Cessna is equipped with a special measuring device. the Met Pod. It is mounted externally on the aircraft and was specifically developed for high accurate measurements of pressure, temperature, wind and humidity.
Beyond
pure weather forecasting, the DLR were also concerned with how boundary layer flows affect our energy production, such as wind energy, and how turbulence over the Alps impacts aviation. Gravity waves can induce turbulence, which can make flights less comfortable.
The project also examines how small-scale turbulence connects with large airflows. Measurement drones are also deployed.
Was mich jetzt sozusagen auch motiviert hat, auch in ein bestimmtes Seitental zu gehen und mit Kollegen.
What also motivated me to go into a particular side valley and collaborate with colleagues from the German Aerospace Centre DLR is that we've already observed the interaction of different wind systems here. On one hand, there's the firm wind blowing over the Geiseljoch Pass and interacting with the local wind flow in the valley, leading to mixing processes. We've already studied this to some extent in a preliminary campaign and have now gone all out in the main campaign, investigating it in detail with drones and remote sensing to understand how this flow works and how it influences exchange processes. This drives me, and I believe we've been very successful in collecting excellent data.
Wir waren diesbezüglich sehr erfolgreich, dass wir sehr gute Daten gesammelt haben.
This data, along with that from many other working groups, measuring stations, aircraft and weather balloons, must now be processed. Hundreds of thousands of measurements form vast datasets that will be analysed using supercomputers and AI.
Thanks to TEAMx, we can now refine our weather forecast models, for example, making much better predictions for valley fog or air quality, and we can participate in international model comparisons.
The year of measurements and its intensive campaigns is over, but international collaboration continues.
It's very exciting to work with other colleagues because all of the problems that we are facing with understanding these really complex processes such as we have in the atmosphere, they really need a lot of people to come together and to think about them from different perspectives, from different methodologies. So this exchange that we have through TEAMx is absolutely amazing. We can actually finally answer these kind of questions. We can also bring different methods, such as, for example, this novel Lidar system that we had on one of the aircraft, which was brought by the KIT from Germany. And then also with our network of towers, we also collaborated with the French colleagues who brought their instruments. So it is very nice because it was a very great atmosphere of really, we are here together to try to answer these exciting, complex questions.
Also TEAMx ist ja ein bottom-up finanziertes Programm, das heißt jeder und jede...
TEAMx is a bottom-up funded program. This means that each group has its own funding. And in all these projects, people are employed, whether postdocs or mostly PhD students, and they'll now begin their own evaluations. Experience shows that the main results from such a large program will be generated over the next 5 years.
5 Jahre, die Hauptresultate generieren werden.
The goal of TEAMx is also to ensure that this data is not only shared among ourselves, but also made accessible to the public, so that other research institutions or scientists who are not directly involved in the measurement campaign can also work with the data.
The individual working groups have very different focuses. Scientists aim for a better understanding of what happens in the atmosphere above the mountains. Weather services seek better climate and weather forecasts. However, it will still be several years before this benefits us when hiking or skiing.